The second type of average atomic mass problem is what we're going to look at here today. The first example that we went through used the masses and percentages to get the average atomic mass, which we could confirm on our periodic table. In a lot of cases, we're working on a different type of problem using the same average atomic mass problem equation, but not finding the average itself. We're actually going to be given the average atomic mass in this type of problem, and we'll turn around and figure out how much of each of the two relevant isotopes of that element are there out there. In other words, what are those percentages? We're going to find for the percentages instead of finding for the average. You'll probably find that this type of problem takes a little more math and isn't terribly difficult at all. The hardest thing you do is distribute, basically, and that's not so bad. But we'll work through this kind of problem, and we'll also be using this in a lab that we'll do in class to sort of see, or a couple labs perhaps, to see if we can use the equation in the more difficult version. I think the first kind is almost pretty straightforward to the point where most everyone can nail those problems if they're at all careful. The second type of problem, the one that we're going to see here, is just a little bit more challenging. So this is on the second practice page that you're getting with equations and problems that are usually worded something like this. And the ones that are in lab will be based on the same sort of idea, although worded quite differently. So the question here says the average atomic mass of gallium is 69.723. Right out of the gates, it's telling us the average. In the last problem, that was our whole point, was solving for that value. So they're telling us that from the get-go here, and so we're solving for something else. It says it is composed of two isotopes, gallium-69 with a mass of 68.926 AMUs, and gallium-71 with a mass of 70.925 AMUs. Now, you might notice here for the first time that our AMU masses of these isotopes are no longer whole numbers. It's an important thing to notice. We'll have an explanation here posted in a little bit as to why, for your next video, as to why the masses of an isotope aren't always simply whole numbers. Up till now, we've been treating them as protons plus neutrons. And of course, if protons is a whole number and neutrons is a whole number, and they'd have to be in an atom because we can't have half of a proton or some fraction of a neutron, then when we add those whole numbers together, we get a whole number of AMUs. So why here are we getting 68.926 AMUs, for example? There's a couple complications that come into the math, but what it does, and the good news is that it gives us more precision in our masses, and we can keep more significant figures, and we can get better quality in our answers. So we're measuring more precisely here. How we were allowed to measure more precisely, despite the fact that we seem to be counting objects toward these AMUs, those protons and neutrons, is a different video discussion. So for now, we're going to use the masses you see here in the parentheses as the precise actual masses, atomic masses of the two isotopes of gallium in question. So the question asks, what are the relative abundances? In other words, what are the percentages for these isotopes in naturally occurring samples of gallium? So if I went in the world and found a sample of gallium or in a bottle in the stockroom, in that bottle of gallium, we're saying there would be two isotopes of it, gallium-69 and gallium-71, with the masses you see here. The question's asking what percent of that gallium would be gallium-69 and what percent would be gallium-71. So we're going to work through that same equation, but in a little different way. So average atomic mass, as we said in the earlier videos, is mass of the isotope times its percent plus mass of the next isotope times its percent, and so on. We've got two isotopes here, so we're going to use the equation as it's written here. Now, average atomic mass, this large value right after the beginning of the equation, is given to me in the problem. That's here, 69.723 AMUs. So I'm going to start my math with that. 69.723 AMUs is my average. I set that on the left side of the equation all by itself. On the right side of the equation, I need the mass of the first isotope times its percent as a decimal. While the mass of the first isotope is given to me here. It's that precise parenthesis value for gallium-69. We're going to use it as 68.926 AMUs. That's my first isotope's mass. And the percent as a decimal is actually what we're looking for. So when we don't know what we're going to call something or what the value is going to be, we'll go ahead and call it x. You can use any variable you wish. I'll use x because I'm sure most of you would probably choose x. If I asked you what variable you wanted to use, people just kind of gravitate toward x, and we'll stick with that for now. Plus the mass of the second isotope. Well, that's up here as well in the next parentheses, 70.925 AMUs. Times its percent as a decimal. Now, we don't know this one either, but we don't want to necessarily call it y. That's kind of what it is. X and Y. We've seen lots of that in math. Perhaps your math class you're solving for X and Y in various equations. And it's not too difficult to do that. But in this case, we know something about Y. We know something about these two percentages. Remember from an earlier video that these two percentages here, okay, these two percentages have to add up to 100 when written as a percentage. And since in this problem we're writing them as decimals, they have to add up to what? Hopefully you remember that they add up to 1 exactly. So these add up to 1 exactly. 1.00 if you will, but add up to 1. So two percentages will add up to 100, and two percentages written as decimals need to add up to 1. So we know that these two percentages will add up to that 1.00, and therefore if this is x, this first one is x, then the second one has to be the rest of it, which would be whatever's left out of 1, right? So 1 minus x. For example, if x turns out to be 0.2, then the other one has to be 1 minus x, 0.8, right? Because those two percentages have to add up to 1. If the first percentage worked out to be 0.95, then the second one would have to be 1 minus 0.95, or the remaining 0.05, 5%. So the two values here, our x and our 1 minus x, need to add up to 1 at the end. And we're going to solve for x in that way. Now, that's the three words that often scare the heck out of students. Solve for x, getting x by itself, those sort of things that math teachers often say that just freak some people out. But that's really what we're going to do here, is solve for x, and I'll help you through it. So the first thing to do, I think, in this problem is to go ahead and start to distribute things out. All we can really do in this first step is distribute at the end of this equation 70.925 times 1 minus x, distribute it out. So I'm going to rewrite this equation 69.723 on the next line, AMUs, and 68.926 AMUs times x yet, plus 70.925 times 1, hopefully you don't need your calculator for that one, 70.925 AMUs. And then we're also going to take 70.925 times negative x, right? So if we're distributing that out, it's minus 70.925 AMUs x. Now, in the end of our problem, the AMUs will cancel out. Along the way, they're kind of cluttery. So don't worry about those AMUs as being like extra variables or hopefully any more complicated than they need to be. If they really mess you up, if having all those AMUs in there along with the x's really messes you up, you can go ahead and delete them from the beginning of the problem. Just leave AMU off. It's appropriate to leave it there as a label until it cancels itself out in the math, which it will. But in the end, the AMU is going to cancel out. We're not going to have that in our percentages. So if it really clutters up your problem and you prefer to take it out, feel free to just take the AMUs out right now. Don't take the x's. You're going to need those. But take the AMUs out and it'll declutter your problem a little bit for you quite a bit. So at this point, we want to get the x's together. In other words, group-like terms. Hopefully you've heard that in math before. 68.926x and 70.925x. Those can go together. What I also want to do is bring all of my AMU values over to the other side. I'm going to bring this over to the left. So on both sides of this problem, I'm going to subtract 70.925 AMUs and get rid of it over on the right side, but I need to do the same to both sides, 70.925 AMUs over there as well. Now what that'll do, of course, is it'll get rid of it on this side, but on this side I need to take 69.723 minus 70.925. Okay? So 69.723 minus 70.925 gives me negative 1.202 AMUs. Okay? Negative 1.202. And I can keep all those decimal places because of the rules of decimal places on subtraction. Right? So that's negative 1.202 AMUs on this side. And on the other side, what I'm going to go ahead and do at the same time is put these x's together. I have 68.926x and I have 70.925x. So I need to put that in my calculator as 68.926 minus, 68.926 minus 70.925. And that gives me negative 1.999. All right, so I'm going to bring that into my problem. Negative 1.999 AMU x. So all I've really done there in that step is I've put this value together with this value. I subtracted 68.926 minus 70.925 and put those together to get this, okay, here. Put those two values together. So this came in and joined up with this to give me my value on the right side of the equation. So now all that's left is to get x by itself. And so I'm going to divide both sides by negative 1.99 AMUs. And this is when those darn AMUs will disappear. Divide both sides by negative 1.999 AMUs. And that will get rid of all this. This is going to vanish when I do that because it's going to cancel itself out. And over on the left side, my AMUs will also cancel themselves out. What am I left with? Let's punch this value into our calculator and see what we get. I get negative 1.202 divided by 1.999. And my calculator tells me that that's 0.6013 and so on. There's a whole bunch of other values behind it. Now I'm going to divide those two numbers. Each of those has 4 significant figures. So my answer can also have 4 significant figures. And so to round that off to have 4, we can take it to 0.6013. And that would have 4 significant figures, yes? So x equals 0.6013. Now, a lot of times in math class, we get to x. And we say, yeah, I got x, but what the heck is it, right? It's important to keep track of what x represents. In this problem, x represents the percent abundance of the first isotope written as a decimal. So we've taken back to the beginning of our problem, x, and put it in place here as the percent of gallium-69, this first isotope. And 1 minus x was the percent of gallium-71, our heavier isotope. So this is essentially a percent written as a decimal. X as 0.6013 is a percentage written as a decimal. Now remember, when we write percentages as decimals, we move the decimal over twice. 0.6013 represents a percentage. Well, what is that percentage? Hopefully you can look at it and see that 0.6013 is the same as 60.13%. Okay, 0.6013 written back into percentage form is 60.13%. So in other words, in this problem, x is 60.13%, or of all the gallium in the universe, 60.13% of it has a mass of 69 AMUs, is gallium-69. And all the rest of the gallium in the universe is gallium-71. So what's the rest? Well, we take that away from 100 to get the answer. So 100 minus 60.13% gives me 39.87%. 39.87% of all the gallium in the universe is gallium-71. Notice it's not 50-50. When there are two isotopes, it's really never 50-50. It's sort of by chance, the way that atoms assembled, back when atoms assembled, and when the elements formed from the dust of stellar evolution and planetary evolution and all the stuff in the cosmos that you need to study about in a physics and astronomy class. But when they assemble, they do so very randomly. And so in the end, 60.13% of the galliums assembled up as gallium-69, and the rest, 39.87%, came together as gallium-71. Now, there may be some nuclear stability that makes some of them more dominant than others and so forth, and some elements form as other elements decay by radioactive decay. And so there's lots of complications as to why is 60% of it gallium-69. That why is a much bigger question than we need to answer. But for now, we can calculate out through a math problem like this that gallium-69 is the dominant isotope, 60.13%. About 3 out of 5 isotopes of gallium are gallium-69, and the other 39.87% is gallium-71. Now, as you look at that problem, that might be a lot of math, huh? But really all we did was take the equation that was given in your notes for average atomic mass and plugged in what we knew. We were given the average atomic mass, we were given the mass of the first and the second isotopes, and we put those into place. And what we didn't know were those percentages, so we called the first one x, and the second one 1 minus x. That's probably the key step to the problem, is recognizing that those two percentages written as decimals need to add up to 1. Therefore, if this one is x, then the other one is whatever's left, the rest of it, 1 minus x. And in this case, the first one turned out to be 0.6013. The rest of it was 0.3987, or 39.87%. There's a lot going on in that problem. The math isn't tough, but man, when you get all those variables and those AMUs and things in there, it looks like a big complicated mess, which is why we're working through more of these in class, with this one hopefully written down in your pocket. We'll definitely be going through more of these, and I can fairly say that I think for more students than any other kind of problem throughout the year, an average atomic mass problem of this kind with x and 1 minus x is probably the hardest math problem that we do all year. If you can get through these problems, I think the rest of what we do in chemistry is mathematically much more simple than this. And this is probably the toughest thing on your plate as far as math problems go. So if you made it through it, you're in great shape. And if you didn't, fear not, we're working through more of them in class. And once you've survived these, the rest is pretty smooth sailing. Fingers crossed. We'll work on more of these in class. Hang on to it for now. Thanks for listening. We'll see you next time.